Okay, so in this tutorial, we're going to go ahead and write up some code that's going to utilize the digital to analog converter on the KL25Z. And what we're going to do with this is we're going to make it so the digital analog converter is going to output a voltage, and that's going to steadily increase, and then it's going to steadily decrease. So let's go ahead and get started with this. So we're going to go ahead and make a new program, and we're going to go ahead and name this. We're going to name this DAC test. Digital to analog converter test. Now, you can use the empty program that Max did in the original few tutorials, but there's also an advantage of just using one of the previous templates, where the previous templates has already some sample code up there running, working, and it also provides the actual mBed library in the program, so you don't actually have to go ahead and take all the steps to import it again. So we're going to go ahead and just get the first one. The first one just pretty much blinks an LED on and off. And let's go ahead and create this program. All right, so we have that. You can clearly see we have the mBed libraries already incorporated in this program. And so now we're going to go ahead and check out this main.c++ file. So as you can see, it's the original code. It just pretty much assigns an LED and it blinks it on and off. So what we're going to do is we're going to go ahead and just delete everything that we don't want. So we don't need anything in the while loop. And we also don't want this as well for the sake of this tutorial, which is going to utilize, it said, the digital to analog converter. So we already have an empty while loop, which we're going to be utilizing soon. But with this, to use the digital to analog converter, we're going to use a class called AnalogOut. And what this pretty much does, it's going to instantiate one of the digital to analog converters on your microcontroller. And the way that it works is you're first going to name it something. So we're going to call it DAC, and you have to assign it the correct pin. So in this case, the only digital to analog converter on the KL25Z is the PTE30. We go ahead and assign that PTE30 as the digital to analog converter. And the way that this works is you pretty much assign it a value. So like the DAC is equal to 0. It's a float value, so it's 0.0F. And the idea is 0 is equal to 0 volts, and 1.0 is equal to 3.3 volts. So the digital analog converter can take in only a value between 0 and 1. And in between any of that will be a subdivision of 3.3 volts. So say for instance, if you say 0.5, it'll actually make 1.65 volts or something very close to that. And so the idea behind this is that the code underlying this is it's going to get that float value and it's going to convert it into some sort of 12-bit value. So it's going to round to as close as it can to some sort of 12-bit value. And that 12-bit value is what it's actually going to be using to output this voltage signal. And so with that in mind, we're going to go ahead and get started with the while loop. So first off, we want to make it so that it increases steadily. So one step should be to increase the voltage steadily from 0 volts to 3.3 volts. And another part is it should decrease the voltage steadily from 3.3 volts to 0 volts. So both of these are going to require a for loop, so we're going to go ahead and write up a for loop to do this. So the way that it works in C is you say for, you're going to assign some value inside that's going to be counting up or counting down, and we're going to assign it a float value. So float, and initialize it so that it's going to start at 0 because we want to make this start at 0 volts. And then with that, we're going to go ahead and set the limit of how many times it's going to count up. So we're going to make it so that that the float value, float j, we're going to call it float I. So float I is equal to a 0.0f, just to make it so that the compiler is friendly with this, so it interprets that this is a float value. That's the reason why you put f after every type of number for floats. And then we're going to say that I is going to be less than or equal to 1.0f. So it's going to be, we're going to make sure that the value I that's going to be increased or decreased is going to be less than 1. And with every step in this loop, we're going to go ahead and increase the value of I by some set float value. So we're going to go ahead and arbitrarily select some float value here. Okay, so inside this, what this pretty much is going to do, we're going to pretty much assign the analog output to the float value that's going to be gradually incremented. And we're going to make it wait for each step, we're going to make it wait for some amount of time. So we're going to make it wait for roughly a tenth of a millisecond before each operation. And so that's what 0.0001 is. So with this, what this pretty much does in this for loop is it's first going to start I to 0, and then it's going to run this loop once when I is equal to 0. So the digital analog converter is going to get 0, and then it's going to wait 0.001 seconds, or a tenth of a millisecond. And then it's going to redo this again, and it's going to increment I by this value. So instead of actually being I being 0, it's now going to be this value, and going to run this again, and it's going to increment again. So it's going to be 0.002, 0.003, and it's going to keep going up gradually and gradually as we go. Okay, so decrease the voltage steadily from 3.3 volts to 0 volts is also going to require a for loop. So just for the sake of time, we're going to go ahead and just copy paste what I previously have and put it under here. And so we're going to make a few minor changes to this. So the first change is just for the sake of making things clear, I like to make it so that my variables in my for loops use different types of variable names. So I'm going to go ahead and call everything j. You don't have to do this, but I just like to do it just to make sure that my code is understandable and nothing ever seems to mess up on anything else. So float j, because it's at 3.3 volts initially, because the previous one sets it up to 1, we're going to go ahead and make it so that it's going to be initialized to 1. And because it's going to be decreasing, we're going to make it so that it's going to keep running this for loop as long as if it's greater than 0, greater than or equal to 0. And instead of incrementing it, we're actually going to decrease it for each for loop. So we're going to go ahead, instead of plus equals, it's actually going to be minus equals. And so that's pretty much all that you have to change for this for loop. What's going to happen, so we're going to go ahead and just look through this again. So this is going to run continuously because it's in a while loop. And the for loop is, what it's going to do is it's going to start off at 0 and then count up to 1. And it's going to do this gradually with a step size of this much. So it's going to run this 10,000 times, and with each loop, it's going to increment I by this much, and then it's going to assign that to the digital to analog converter, and the digital to analog converter is going to convert that into some voltage level, and it's going to output that, and then it's going to wait roughly this much, so a tenth of a millisecond. Okay, so once it reaches up to 3.3 volts, it's going to decrease it in this for loop in the exact same manner as the previous for loop, but instead it's going to start at 1, and then it's going to count down all the way down to 0 volts. So let's go ahead and compile this and go ahead and run it on the KL25Z. Okay, so I already have the mBed powered up for the digital to analog converter, and all we're going to do now is we're going to grab some of these oscilloscope probes, and we're going to go ahead and attach some wires onto them so we can go ahead and probe the microcontroller. So this is going to be connected to ground, so we're going to go ahead and find the ground pin on this. And the ground pin is located right over here. So we're going to go ahead and put that right here. And then we're going to go ahead and connect this to the digital to analog pin. So it's actually located PTE30, which is roughly right here. So we're going to go ahead and put that right here. And I already have the oscilloscope turned on, so I'm going to go ahead and just zoom out and look at the oscilloscope. You can actually see a triangle-shaped waveform. So this is what's being output on the mBed microcontroller. So the KL25Z is on the digital analog converter. It's steadily increasing the voltage and decreasing the voltage as we programmed it to do. You can, with this digital analog converter, make a variety of different types of signals. All you have to do is you just have to output the right voltage at the right respective type of time. I've seen people make sine waves with this. I've seen people make sawtooth waves with this as well. You can do a variety of different things with the digital to analog converter.